Okay, so the topic is time domain specifications. We have a control system which we want to control, and we want it to respond nicely to our commands and reject disturbances. What do we mean by commanding, responding nicely? Let me give you an example. Let's say we use a robot, a very simple robot arm. Okay, it's a robot, but don't think it's like an industrial robot. This is just a toy robot arm. It shouldn't be like this. It is a metal arm, let's say, which we rotate using a motor. You apply a voltage to one end, and there is a, let's say, a control box here. Let's not talk about the details of this control box. This arm, just like the, let's say, door of like a door, it rotates an angle of theta. And you might want it to rotate, let's say, starting from here, rotate 90 degrees and stop. Okay? So you want the arm to be rotate like this and stop. That is, if you have a door, when you push a button, the door opens 90 degrees and stops. Okay? It is actually a, quite reasonable command. So you give a command for it to, let's say we want the arm to rotate 90 degrees and stop. Okay. So this is a step response. We give a command of 90 degrees, and then the arm rotates 90 degrees and stops, but it might do the following. It might, overshoot a little bit. It might come to, 120 degrees and come back to 90 degrees. So our control system here is something like this. There is a desired value of theta. There is the control, which we don't know what this is for the time being. There is the arm. Arm has a theta. We apply a torque to the arm through the control. That is the motor. Well, maybe I should put a motor here as well. So this is theta, supposedly. We measure it. Let's put the measurement in also. This is theta. Measurement basically measures theta. This is theta measured, let's say. This is the error. This is U. This is torque. This is theta. Okay. This is a very typical control system. You want it to rotate 90 degrees, let's say, or 180 degrees, or whatever degrees, and the arm rotates as you desire. Okay? So the typical response would be this. This is theta of t. If you design the control system well, this is the time response. This is the desired value of theta, which is like 90 degrees. Let's say it doesn't have to be 90 degrees. And then the response will be, there are a family of responses actually. This is a possible response. This is a possible response. This is a possible response or something. Or you might even have something like this. Okay, all these are possible. Well, some of these responses are good, some of them are not so good. Which ones are good and which ones are worse? What do we want from this system, and how do we quantify a good design for such a system? That is, what is a good response? Good response should be, first of all, it should be fast, right? You know, as fast as possible. A slow response is not so good because, you know, it will take a long time. And if possible, we want little oscillation. Not too much oscillations. And we definitely want no steady state error. Steady state error. Actually, I didn't draw a response with steady state error here. Let me draw one. For example, you might have a response like this one. Let's say this one would have a steady state error, this one. This is a steady state error. Steady state error means you want the system to rotate 90 degrees, the door or the arm to rotate 90 degrees, but then it rotates only 60 degrees in the end. And that's not what we want. That is bad response, definitely. Okay, so we want to have these kind of things, and we want to quantify this. We want to quantify the good response by the following parameters. Okay. If we quantify a good response, let's say, right. Let me just draw a step response. T. This is y of t, a general y. This is the steady state value which we want, okay? First of all, there should be no steady state error. Secondly, let's plot it here. This is the response, right? First of all, the system should be fast, and that it can be measured by the time it settles, okay? This is called the TS, which I will call approximately. That is when it reaches the 99% of the steady state. I can call it the settling time. Okay. Another time that is important is the time it reaches at the peak. This distance is called TP. Peak time. There is another time here in which the system response, looks odd in the beginning, but there is a logic to it. The time it takes to rise from, let's say, 10% to 90%, this is called TR, is the rise time. Let's say
Hujam, I have a question.
yes.
Hujam, so the rise time is basically where it's smooth, the line is constant, or is it a different rule?
No, it's you take it from the 10% of the steady state response to 90%. This can be arbitrary. It can be from 0% to 90%, or 10% to, I don't know, 75%. But this is a standard. I don't know why people have selected 10 to 90 of the.
Okay, Hujam, thank you.
TR is another thing. Another important thing is this overshoot. This quantity, which we will call MP, is called the maximum overshoot. As you see, we want all of these quantities, TS, TP, TR, rise time, and maximum overshoot, MP, as small as possible. So we want TS, TP, TR, P as small as possible. So what would be the best response, in a sense? The best response would be this. You put a step input on the system, and your system responds like this. That is, it acts as a zeroth order system, okay? This green line would be the best response, but with physical systems, this is not possible, okay? You have to have a little bit of delay and some oscillation. Otherwise, you cannot have a physical system that responds instantly. So if you try to obtain that, you have to increase the controller gain too much, but that causes, again, problems like stability or saturation and so on. So we want a reasonable, fast system with little, let's say, oscillation, as much as possible, okay? It might not be completely possible to have, you cannot have this green line. This is unrealistic. A realistic one would be a line that is this red line with parameters that are kind of minimized, if possible. Okay. One more thing, the maximum overshoot, by the way, is defined as follows. Maximum overshoot is, if you want to define it in why the response at the peak time okay, minus the response at infinity time divided by response at infinity time. That is the maximum overshoot. But if you want the percent overshoot, you have to multiply by, this is percent max overshoot. So, settling time is usually selected as, let's say 1 or 2%, 1%. Peak time is, as you know, the peak value. Rise time, I have defined it, and so on. This is valid for all kinds of systems. That is, you can have a high order system and still have this well, we can define these parameters. For example, you can say, I want a system that settles in 2 seconds and has a maximum overshoot of 10%, for example. So the specification might be something like this. So specification, let's say settling time is 2 seconds and the maximum overshoot is 10%, 20%, etc. Whether you can achieve this or not is another problem, but you can specify it. Like, I want a system that settles in 1 second and has an overshoot of 20% or something. As we said, there is no general formula for these specifications. You cannot, these specifications cannot be defined for general systems, but we can define them, these specifications, for second order systems. For second order systems. We can define them in terms of the system parameters, okay? If you approximate your control system, the closed loop transfer function, by a second order system, like this one, omega n squared, s squared plus 2 zeta omega n s plus omega n squared. As you remember, you see the steady state gain of this system is 1, okay? Because if you have a control system, if you design it properly, the steady state gain of that control system will be 1, so that there will be no steady state error. So let's say that we approximate our closed loop system with this transfer function. Okay? So, and also let's assume that let's say 0 is less than zeta less than 1. That is an underdamped system, which is reasonable. We have an underdamped system. Okay. So the poles are minus zeta omega n plus minus j omega n root minus s squared. Okay. And the response of this system to a unit step input, we are looking at unit step input, as you remember. So the unit step response of such a system is y of t is 1 minus, I have written this down, zeta omega n t plus some phase angle, phi, phi being tangent inverse of squared over. So, from this equation, actually, we can derive all the specifications about. So, MP, let's say TP, TR, TS can be derived from here. Okay. This will be the values we will be deriving will be valid for second order systems only, unfortunately, but it gives a good guideline for other systems as well. How do we derive it? The response is like this, as you remember. This is y of t. Well, we want the first peak, as you see. The peaks are the derivative set y dot of t to 0, okay? The derivatives are 0, and solve for the time value. The lowest solution will be the get TP. The peak time will be the lowest solution to this y dot of t, okay? And if you do that, I'm not going to do it because it's just taking derivatives and so on. TP will be, as you can expect, pi over the damped natural frequency, which is pi over omega n root 1 minus theta squared. That will be your peak time. Then the maximum overshoot, MP, can be obtained from, or let's say, yeah, I can say that MP would be equal to what would it be? Y at TP minus y at infinity divided by y at infinity, but these are ones, so this is y at TP minus 1 divided by 1. So you can find it, and actually solving, you are going to get the following. MP is going to be e to the minus pi zeta divided by 1 minus zeta squared. Okay. This will be the maximum overshoot. This is maximum overshoot, not percent maximum overshoot. If you want the percent, you have to multiply this with 100. Okay. Then the settling time would be something like 4.0 times zeta omega n. This is 2% criterion, or Ts equals 4.6 divided by zeta omega n. This is 1%. That is, you reach the 1% of the steady state value. If you want to use 1%, you use 4.6. If you want to use 2%, you use 4 over zeta omega n. Zeta omega n is the real part of the poles, as you remember. This is, derived from the response. And finally, the rise time. This is kind of empirical. This will be 1.8 divided by omega n. The rise time is from 10% of the steady state to 90%. So for second order systems, we have formulas. So the maximum overshoot is e to the minus, what was it, pi zeta divided by root 1 minus zeta squared. And you see that this is only a function of zeta, okay? Then the peak time, for example, Tp is pi over omega d, was it? Damped natural frequency. The settling time, sorry, what was it? Let's say it's 4 divided by zeta omega n, which is a function of zeta and omega n. And the rise time would be 1.8 divided by omega n. It is a function of the natural frequency only. Okay? So when you define certain parameters like these ones, you can, for a second order system, you can exactly solve for the necessary parameters in your system. For example, if you define, let's say, the maximum overshoot and the settling time, let's say, you can solve for the natural frequency and the damping ratio, and then from there you can find the control gains. But for higher order systems, you might have to resort to trial and error procedures. By the way, let me also give you something. This is MP versus MP was a function of zeta, as you see.
Hujam, I have a question.
Yes.
Hujam, in the settling time, you're using TS as zeta omega n. So are there like two variables that we're considering, or are you considering them as one variable?
Zeta is damping ratio, omega n is the natural frequency. Why?
So we're just dealing with one variable.
Well, zeta times omega n is one variable, yes. But
okay.
At least two variables, you are right. Now, if you start from this maximum overshoot, when the damping ratio is 0, the maximum overshoot would be actually 100%, okay? Or it would be 1, because it's an undamped system. And when it is, let's say, 0.2, you get to something like 50%. Okay. Which is still not too good. And then it just goes like, let's say this is 1. So it is a curve that is like this, okay? But for, this is e to the something is a difficult thing. You can approximate this 0 less than zeta less than 0.6 or something like this, the maximum overshoot can be approximated by 1 minus zeta over 0.6, if you like. Okay. So it is a more or less a straight line curve, as you see here. Oh, so I don't know if we have enough time for a problem. Let me just give you a very rather simple problem. Let's say this is R, is the reference input, and this is a closed loop system with let's say that this is a closed loop system. This is Y, this is R, this is minus negative feedback, this is U. So you have a closed loop system like this one, combine controller and the system together. This might be a motor control system or something like this. But this system has a response like this one. Closed loop step response, y of t versus t. Okay, the peak is at 3 seconds, and this value we have, here's another color here. Is 0.254. Okay, this distance is 0.254. So it's the maximum overshoot and the peak time. So this is the unit step response of the closed loop system. Step response. So what it asks is determine K and T values. From this response. Okay. So we see that from the step response, the peak time is 3 seconds. Okay, 3 seconds, which is equal to pi over omega d of the, by the way, before that, pi over omega d. But this system, from the block diagram, if I, reduce it to a r over y, it is going to be the following. Y is equal to K over S times Ts plus 1 U, right? But what is U? It is R minus Y, isn't it? It is R minus Y, yes.
This pi over WD and like the other formula you wrote, are these general formula?
No, this is valid only for second order systems, and I will show you that this ends up being a second order system.
No, I mean, is this general for second order systems?
Yes, these formulas I have derived are valid only for second order systems.
But all of the second order systems, they work?
Yes, All of the
Okay.
second order systems, they work, yes.
Thanks, Hocam.
Well, with no zeros. The second
Thanks,
order
Hocam.
system should not have a zero. So r minus y. So you have what do we have? In y parentheses, 1 minus 1 over s times s plus 1 y is equal to k. So k here. So this is a plus, I'm sorry, this is a plus. So you get ts squared plus s plus k times y is equal to k r, right? So y of s over r of s, which is the closed loop transfer function, is k over ts squared plus s plus k. Or you can write this as, if you like, k over t divided by s squared plus 1 over ts plus k over t. Okay, now this is a second order, standard second order system. It is omega n squared, s squared plus 2 zeta omega n s plus omega n squared, as you see. Okay, where omega n squared is k over t, and 2 zeta omega n is 1 over t. Okay, let's continue from here. We said that the peak time, Tp, was pi over omega d, which is pi over omega n root 1 minus zeta squared. Also, the maximum overshoot is 0.254, which is e to the, let's say, minus pi zeta root 1 minus zeta squared. What do? You take ln's of these. Ln of 0.254 is equal to minus pi zeta over root 1 minus zeta squared. And you can solve for zeta here. It's not too hard. Or you can use the approximate formula. It won't be too different, I suppose. And from here you get that the damping ratio is going to be 0.4. Okay. So damping, we have found it. The TP is equal to 3 seconds is equal to pi over omega n root 1 minus 0.4 squared, from which you can solve for omega n. That will be what? 1.14. So the natural frequency is found. The only thing we need is we wanted k and t. As you remember, t was, well, 2 zeta omega n was 1 over 2. So T is 1 over 2 zeta omega n. So 1 over 2 times 0.4 times 143. So the T value is 1.094 and K is omega n squared. T omega n squared was what? Times T minus T, yeah. So these are the results, okay? So it's a kind of a simple problem, but it illustrates things in the system rather nicely. We will go through our robot arm example the next time, and I'll try to show you how it works, how you can design a controller using that, and the specifications for that system.